Okay, good day, class. So, this is our subject, mechanical vibration or vibration engineering. So, let's go to chapter 1, fundamental of vibration. So, by the way, I am Engineer Redentor Raila. I am a professional mechanical engineer with a practice of more than 25 years now. And I'm tasked to um, instruct you as part-time instructor of CTU. No? So begin with, this is our course outline, fundamentals of vibration, second, free vibration of single DOF systems, no? Degrees of freedom, no? Harmonically excited vibration, vibration under general forcing conditions, 2 DOF system, multi-degree of freedom system, determination of natural frequencies and mode shapes. No? Continuous systems, vibration control, vibration measurement and application. And then number 11, numerical integration methods and vibration analysis. Then 12, finite element method. 13, nonlinear vibration and the random vibration. So under the course outline 1.0, we have 1.1 up to 1.11. That is, we have preliminary remarks, brief story of vibration, importance of the study of vibration, basic concepts of vibration, classification of vibration, vibration analysis procedure, spring element, mass or inertia element, damping elements, harmonic motion, harmonic analysis. So in our day-to-day um, application or the practice of our profession as a mechanical engineer, we're always dealing with machineries, no? And we know for a fact that machines do vibrate, no? And this is why that leads to the development, no, of many um, mechanical systems, no, that become so efficient because of the study of vibration. They were able to come up with rationally or conclusion on how to equip, no, the facility or the equipment with proper with a proper balance, and that passes through the vibration analysis and procedures. No? And from this outline, we can see a lot of machine elements. No? It mentioned there spring, what else? So, a lot more of that. No? We know already what are the different elements of machineries, and even in machine design laid out to us the different types of machine elements. So under the preliminary remarks, we talk about brief story of vibration, examination of vibrations, important rule. No? From this study, we'll be able to know the importance, no, of vibration. Since the time immemorial, vibration is already there and always part of the mechanical development. No? And it's just that recently we've able to put that into pragmatic application, no, under our curriculum in the mechanical engineering um, syllabus. And we have also the definitions and concepts of vibration. So concept of harmonic analysis for general periodic motion. So under the brief history of vibration, we see that around 580 to 500 C before Christ, BC, no? It was Pythagoras, this one. This one, you can see the weight and the string. It's the Greek philosopher. We know that, during our juniors, no? And mathematicians, the first to investigate musical sounds on a scientific basis. But in vibration is um, coupled or somewhat like correlated with the sounds. No? The moment that there's a vibration and it's too much, more than what is standard, more than what is required, it created a sound. No? And you know for a fact that when there's an overrated sound, something might happen next. No, there might something worse that happens to our, for example, in our shafting, in our elements, our flywheel, or whatever brake systems what do we have. Anything that goes beyond the rupture, and it because of a series of expected vibration will lead to disaster or catastrophe or damage. No? But Pythagoras conducted experiment on a vibrating string, no? By using a simple apparatus called a monochord. So this is a monochord. No? So there's a string on that. Developed the concept of pitch. No? So pitch is also related to sound and music. So after that, we have around 350 BC. We have also another famous one, Aristotle, and we have Aristoxenos. So he wrote a three-volume work entitled Elements of Harmony. No? And in 300 BC, we have Euclid, no? Wrote a treatise, Introduction to Harmonics. No? So you know already the harmonics are related to sound. No? When something that creative noise or sound that it develops something like a harmonic. That, but in AD 132, Shang Xing invented the world's first seismograph to measure earthquakes. No? You know already what the the relevant of vibration with regards to earthquake. No, you can imagine the whole world or will experience an earthquake or perhaps somewhere in the Luzon area or even during our earthquake. No, and way back 2013 we have an earthquake that really affected some of our populace. No, and in fact this seismograph will measure no, the rich skill no, of earthquakes. So Zhangjing, if you, you will know this, I think this comes from China, no, Chinaman, no, or whatever related to China. And next we have Galileo Torelli, no, Galileo Galilei. You know already this guy invented the telescope, right? Founder of modern experimental science, started experimenting on simple pendulum. So pendulum is also a balance moving mechanism like a clock that we call it pendulum. It's going back and forth to and fro. So it also created vibration. It's kind of vibration that when took place will act in motion like a pendulum. Published a book, Discourses Concerning Two New Sciences, no? In 1638. So we go now 16th century. Describing resonance, frequency, length, tension, and density of vibrating stitch string. So this is now the beginning of resonance and frequency cycles per second, and length, the x and y axis, the tension, they talk about stress and stresses, deformation and density, of a vibrating stitch string. But in the year 1635 to 17th century, we have Robert Hooke. So what did he do? He found relationship between pitch and frequency of vibration of a string. No? So again, we are now relating to vibration string, creating a sound, and somewhat like there's a pitch and frequency of vibration. Frequency is the how many times the creation of sound will develop and would repeat itself. It's a repetition. No? So later on, we'll go to the meaning of vibration. Okay, we have also Joseph Sauvier, no? In 16th to 17th century. What did he do? Coined the word acoustics for the science of sound. No? So this is the very first time the word acoustics. No? We have acoustics engineering, vibration engineering, although they are related to sounds, but acoustics um, is more close to the science of sounds or engineering of sound. Bounded nodes, loops, harmonics, and the fundamental frequency. Calculated the frequency of a string from the measured sag of its middle point. That Joseph Sobuya. But we also have a famous one, Sir Isaac Newton, for nuclear, na? Publishes his monumental work, Philosophia Naturalis Principia Mathematica in 1686, discovering true laws of motion. You remember that? The first, second, and third laws of motion, that's what we're always using, no, in our law of physics, no? And even in our thermodynamic and other uh, engineering sciences. Brief history of aviation. We have Joseph Lagrange, 1736 to 1813, found the analytical solution of breathing string and the wave equation. No? So here's now the improvement. We have now the wave equation. And we have Semyon Poisson. No? If you can recall, Poisson solved the problem of aviation of a rectangular flexible membrane. So even in a membrane, no? Rectangular, there's a problem of vibration on that. R.F.E. Cleves, 1872, studied the vibration of circular membrane. After the rectangular, we have the circular membrane. You have also Lord Baron Rayleigh method used to find frequency of vibration, no, of a conservative system and multiple natural frequencies. So it starts now the more of the vibration, no, with regards to its frequency and even multiple natural frequencies. Not only that, even the recent 1902, we have Mr. Prum investigated the importance of torsional vibration. No? We come to hear a lot of torsional stresses, and now we have torsional vibration is coming out more often in the board exam, no? In the design of propeller shaft of steamships. No? Because this is very important. No? Just like the World War One and One Two, they use a lot of ships, no, and these are run by steam, and of course, this coupled with propeller shafts. And in order to be more proficient and efficient, we have to study by abbreviation study, leading to torsional aspect of the machine elements, no. So that's the study of Fram, no, and because of that, as you can see, the outcome of the war is so devastating, no? So that there are a lot of familiar um, encounters like the submarines and even the United Kingdom ships, no, toppled down because of these submarines, no. So these are coupled with study on torsional vibration. Aurel Stodola in now 1943, no, contributed to the study of vibration of beams, no, even the beams, no, beams, structural beams like in the buildings, no, there's a vibration on that, and you can project and even analyze, no, um, beforehand, no, that the beam is operating with balance or operating with abnormality. No, you can analyze this kind of elements. We have also the plates and membranes. No? Develop a method for analyzing vibrating beams, which is applicable to turbine blades. No? Can you imagine that? So our blades are supported with beams, structural beams, and without these beams, no, how can you all, secure the weight of these big turbine blades in our turbine plants? No? So that's how Ariel contributed to the Brevisian study, no, with regards to beams. We have also CGP de Laval, that's around 1845, 1930. What does he contributed? He presented a practical solution to the problem of Brevisian of an unbalanced rotating disk. Now, there's a lot of rotating, no, structure or mechanism. So this kind of unbalanced rotating disk is very important because as we can see, we have a lot of hydrodynamic balancing of rotating shafts, no? And because of these, will lead to practical solution of vibration problems, no? And in fact, we have a lot of boilers, blowers, and fans, and even mechanical shafts for not only for air and water transport, but also for land transport, and this provides for engine um, what you call this stability now with regard to vibration requirement and prevent anything harm or danger uh, to our commuters. 1892, we have Lyapunov. This is a very great history of vibration. Laid the foundation of modern stability theory, which is applicable to all types of dynamical system. Uh, that is stability theory. No? That is also related to vibration. In 1920, Dofling and Van der Pol brought the first definite solution into the theory of nonlinear vibration. No? Part of our discussion is nonlinear vibration. No? And draw attention to its important engineering. Introduction of the correlation function by Taylor. In 1950, advent of high-speed digital computers generate approximate solution. Even computers high speed are also related to vibration. No? So in 1950s, developed finite element method (FEM), no? Enabled engineers to conduct numerical detailed vibration analysis. So this is uh, timely now that the high uh, level of engineering study is FEM, finite element method, used to analyze engineering complex, no? Like vibration analysis for vehicular and structural system, which displays thousands of degrees of freedom with the aid of computers. No? Uh, so these are studied by Turner, Clough, Martin, and Tapp, presented the finite element method as known today. No? So this is very important. So what is the importance of study of vibration? Why we study vibration? First, can lead to excessive deflections and failure on the machine. So this is very, very practical. No? So sometimes over vibration and create excess deflection and fail, no? Fail the machine and structure. So it will rupture and go beyond the safety factor, and the life is ruined practically because of vibration. To reduce vibration through proper design of machine. No? This is why we need to design machines and even study the material strength and quality. No? And even their mounting supports are very important to um, get the moment of inertia and be able to find the right no, uh, proportion of mounting the actual spacing or the the concentration of the weight with a given inertia. To utilize profitably in several consumer and industrial applications. To improve the efficiency of certain machining, casting, forging, and welding processes. No? To stimulate earthquakes for geological research and conduct studies in design of nuclear reactors. So can you imagine that? Even in vibration, we can understand, no, happening of earthquakes for geological research. No? Now and then we have NASA, no, we have Pag-asa, no, to determine the incoming no, earthquakes, and we have also the nuclear group, no, institute in design of nuclear reactors. No? And basic concept of vibration, we have vibration, it's the meaning, no? Any motion that repeats itself after an interval of time. So there is always a time, no? And the flexibility or the guaranteed no life expectancy of material will depend upon the minimum amount of time that vibration repeat itself. No? Vibration system consists of spring or elasticity, mass, or damper. So always be well known. Always make sure to memorize that these are the concepts of components of vibratory system. No? That is elasticity, or the mass or weight or inertia, and damper. No? Dampening unit, dampening um, system. So involves transfer of potential energy to kinetic energy and vice versa. So we can see that the system or even the component itself will start from potential energy, and when it runs, it acquires kinetic energy and vice versa. If it comes to halt or stop, then it goes back to potential energy. So there's a basic concept of vibration with regard to degrees of freedom. No? So what is the degrees of freedom? Minimum number of independent coordinates required to determine complete the position of all part of system at any instant of time, in any instant of time. So like a pendulum, like this, no, moving back and forth. So these are the degrees of freedom. No, you have degrees of freedom here. Example of single degree of freedom. So single only this one, no. So you can create an angle here and go back to the other one, 2, and 3. No? So there's a distance is for this one at horizontal axis with the datum with regard to y, regard to if this force here is mass times g times acceleration. And regards to slider crank spring mechanism, so this one, no? So it's like a slider crank. So it goes this one with the next, and there's degrees of freedom here. So when it moves somewhere over there because of this uh, spring, no? So it creates something like this, no? Okay. So another example is the spring mass system. So there's a spring here. So if the mass is moving that way at a certain distance, so we have a ski spring distribution. So this single degree of freedom is just single. It's not double. It's only single here. You have also torsional system and create rotation. So there's an angle from the datum here. So you can expect vibration or because of the rotation of the this torsional system. And another thing is the 2 degree of freedom system. No? So we have 2 degree, and this one 2 degree because we have reflection 1, reflection 2. We have here 1 and 2, and what else here? This one x and y. So x and y in the upper part. So there's a spring here, but the force is acting both sides. No? So we have a distance here. We have also a distance here. No? So you know already what's happening to this kind of load here, acting in degrees. No? That's why they call it 2 degrees of freedom system. Next, we have the 3 degrees of freedom. So we have here 1, 2, and 3. No? So there are reactions by the different three masses M1, M1, M2, M3. Same thing with this, we have G1, G2, and K3. This one, K1, K2, and K3, and even K4, no? So these are the 3 degree system. So we have mass 1, M2, and M3, no? So we can apply that later on. These are the basic concepts of vibration. So example of infinite number of degrees of freedom. So let's like this, we have x1, x2, x3. So since this is infinite, so it's continuous, no? Real numbers of degrees of freedom are termed continuous, no? This one. So we can have x1, 2, 3, and 4, 5, 6, 7, and 8, no? Or distributed. Finite numbers. Unlike finite numbers of degrees are termed discrete or lumped parameter, no? So more accurate is obtained by increasing number of degrees of freedom. The more you get, the more results, no? The more it becomes accurate. No? Okay, free vibration. So before that, a system is left to vibrate on its own after an initial disturbance and no external acts on the system. Just like simple pendulum, no? If you act on it initially, it will just continue bouncing and bouncing, no? Without the external force acting on it, no? But unlike force vibration is subject to repeating external force like oscillation arises from these ranges, like the camshaft, no? The main shaft, no? Oscillating. So resonance occurs in the frequency of the external force coincides with one of the natural frequencies. No? If there's a coincides, meaning two of these are working either with the time interval or same interval, it's called resonance. No? frequency, refers to the frequency. It coincides with one another. So next we have undamped vibration. We know energy is lost or dissipated in friction or other resistance during oscillation. So there's no vibration at all, no? Damped vibration when energy is lost or dissipated in friction or other resistance during oscillation. So this is a kind of vibration which being lost or dissipated in friction. But these are the level of tolerable vibration. There are other cases that is more than the standard uh, case, then that the vibration is lost, but at the same time is not providing the type of work, no? The proper work that needed for the mechanical system. Linear vibration. So when all basic components of a vibrator system, i.e. the spring, the mat, and the behave linearly. So again, there are three components, no, of a vibration system, like the flexibility or the spring, no? That's like we see in the degree of freedom. There's a spring deflection. We have the mass M1, M2, M3, and the damper, no? Where the damper, the stand and the dampening, no? Damper means it's being damped to that mass to a certain area, like when you bump to a street or to a post or to the wall, so you are being dumped onto that, no? And if these three things are behaving on the same line, so that is called collinear or linearly. So that's why we have linear vibration. Okay. We have also nonlinear vibration. Any of the components behave non-linearly, no? So the 3 points are not aligned, no? They come to a different locations, no? Or points. We have also deterministic vibration. If the value of or the magnitude of the excitation, force or motion acting on a vibrator is known at any given time, no? So that is deterministic from the word determine, no? You can determine the vibration, no? Or the magnitude of excitation, which is the force or motion at any given time. So this is the process where we have to make analysis on our vibration, no? There are also what we call non-deterministic or random vibration, when the value of excitation at a given time cannot be predicted, no? That's why we need suitable, precise equipment or tools or device to determine random vibration. These are the causes of example of a graph of deterministic, periodic excitation, and random, no? So if deterministic, so you have the same path, no, up and down, but when you compare it to the random, so you cannot trace, no? You cannot determine the path because it's unusual or unexpected, no? So again, the keyword is cannot be predicted, no? Okay, we go to 1.6, the analysis procedure of vibration, no? Of course, we do mathematical modeling, derivation of governing equations, no? Solution of the governing equations, interpretation of the result. This is very, so far, the best part, no, of conducting. This is where vibration engineers are most vital, no, in terms of the application. You are going to be paid by your client by analyzing the vibration, no? Knowing vibration, you will know what is happening internally and externally in your system, just like the turbine, the pumps, um, even the coupling shaft, big machines like generators, no, for the diesel engine and even for the pump itself, no. So you need to locate, no, the cause of the vibration and be able to find a solution, make some resolution and conclusions, no, and recommendation. Example of the modeling of a forging hammer. So if you are going to model a forging hammer, so this gonna look like this. Now you have the soil damping, soil stiffness. So this is dampening and stiffness. Again, there are three vibration, no? Consists of, no, components, the damping and the flexibility and the weight, no, and this is the anvil and the foundation block, no. So this is the tip, no. So once the tip strikes, it goes down, no. So the damping of elastic pad, no, here. So let this be C and E. So there's another stage here and here. So this is now what the end result, no. So we have the sowel, we have the foundation block, and the elastic pad. So this is the anvil, this is the frame, no? And the tip. So this is the force going down here, and check whether the sowel or foundation block, no? So that is a forging hammer. So just need to check whether the testing of certain this foundation. Okay, we are going on to modeling of a motorcycle. No? As I mentioned earlier, that motorcycle are not just built with the design of running, balancing, or whatever the components will have to come out with a better quality, but it has also to consider the developed sequence of three mathematical model. What are the three sequence? No? That really applies the vibration in the vertical direction. No? Again, elasticity of the tires, elasticity of the damping strut. So where is the tire? Here. The strut is here. This one. You are familiar of the strut, no? It create dampening, no? So it will protect you from being no, moved when you strike something like a hard stone, or you go to higher places. This strut will just go up and down, no? It's like uh, very flexible, no? It's flexible. That's why again, the three components: flexibility, elasticity, and dampening of strut. Of course, the masses of the wheel, no? So we have to consider the weight of the wheel. So make sure that it is light, it's made of aluminum or whatever materials that can lighten, no? the 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 motor itself, no? And damping and the mass of the rider. So these are the three, no, important system for mathematical modeling of motorcycle. So you know already there are a lot of manufacturers of motorcycle, and so happen that they refer to all this mathematical modeling system on how to investigate vibration in the vertical direction. So meaning vertical direction, so you will see how the several factors that affects the efficiency of the running of the motor. Now we have the wind, opposite wind, and how does the wind reacts to the moving motors in opposite direction, and even the person or the rider itself. Sometimes the rider will need to incline his body, right? No? In order to no increase the speed. No, it also affects the vibration itself with regard to motor, because if you are wide enough, and then there's a tendency to block the direction, then it also triggers, no, affects the vibration of the motor, no. So it's related. Again, we go back to the components of the vibration system: dampening, weight, and flexibility. Okay, after that we have a solution for that. So this is the answer, no. So just read it, and I think I've mentioned that already. The equivalent damping constant, CEQ, no? So always remember that if you refer to damping, it's CEQ. Include the damping of the struts and the rider, no? So and the equivalent mass includes the mass of the wheel. So and the stiffness is KEQ, no? We have the mass of the wheels and the body. So if you can see from the diagram, is now the MEQ, KEQ, CEQ, dampening and the spring and the mass, no? And you go to 2 degrees deflection, or considering two mass of the rider and mass of the motor, no. So this is now your equation B and C, no. This is the solution of how you make a graph towards the motorcycle, no. Mass of the what's that, MEQ, mass of the rider and the mass of the strut, mass of the wheels, vehicle body, and the rider. No? So review on that. Okay, solution. So how this model can be refined by presenting the masses of the wheels, resistive type, and damping of the struts referred as shown in figure 11.8. In this model, the mass of the vehicle body MB and the mass of the rider MB are shown in the single mass. No? So this one in the single mass. No? So mass of the vehicle and the rider. No? When the SRT as spring constant K and the damping as damping constant of C of the rider are considered the refined model in figure 1.18 can be obtained. So this is the one. No? 1.18D. Okay. So this one D. No? So this is now the combination. Okay, there's another one here, D. So this is the subscript tire, vehicle, wheel, rider, strut equivalent, mass equivalent. Mass of the wheel, mass of the rider, mass of the vehicle. So that's that, but it's now the combination. You can also do it like this, no? Two instead of one MB plus MB, MW. Well, so you have two deflection also. So this equates to this one, but this one with lower, no, lower. What you mean the this one in terms of the spring, because the strength of this one spring is equivalent to the strength of the two spring, and this the dampening is equivalent to two dampening. No? So this is how you consider vibration analysis when you're doing a motorcycle. No? So in order to increase more efficiency, you can build like this. Okay. So in 1.18B to D are not unique. For example, by combining the spring constant of both tire, the masses of both wheel, and the spring and damping of both sides of single concrete, the modulation can be obtained instead of figure 118C. Okay. So we go to spring elements. So this is the formula. Spring force equals Kx, spring stiffness and deformation. No? So that is equation 1.1 linear spring. That is spring force. We have also the work done, U1 over Kx squared. When incremental force is added, so you just add, no? Delta force plus F, or F times X, that subscript, then 1 delta X, no? Or force X dF dx times delta X plus this one, and so on and so forth. No? That is additional force. No? But always remember that is the force, and same thing this as Kx, no? So that's additional force. So when you go to spring elements, so you can see the stress and strain formation, no? So if this is the stress, you have the strain, so this is your yield point. No? Same with force F and the formation X. If you can see it from here, so the applied force is somewhere here and the formation X is over here. So X is x1 minus x2. So where is X is 1? Huh? Okay, x1 minus x2. And force F, you can see here the value of the formation. This is force, this is force Fx, but additional force will be force delta F because F's x. No? So this is additional force increase. So x plus delta x. And this area here will be the kx dp dx, this integration, no? The derivation. Okay, we have another formula. Static reflection is WL3. So that is the weight equals mass times g acceleration times I, no? Moment of inertia divided by E. Young's modulus and spring constant is given by KW over gamma, no? Or 3EI over L. Moment of inertia, 3I. So next, these are Combination of springs, you have key 1, key 2, key 1, key 2, and then the mass supporting a member here. Springs in parallel. Na? If you have a spring constant, that is key 1, key 2 to total key n in parallel, then the equivalent spring constant key EQ is key 1 plus key 2. No? So that's the total equivalent. Key plus 1, key plus 2. So you have also combination of spring in series. No? So if that is in series, that is 1 over key plus 1 over key 1, and so on and so forth. No? That is series. But here we have series key 1, key 2, and then key 1, key 2 here series. And all you have to do is make a fractional ratio and add it. No? So we go now to torsional spring. No? It's very important, especially in the propeller shaft. This is how Boeing, no? 143 and 747 is running efficiently in the mid-air or even the high air, no? Because of proper torsional vibrational analysis. No? So we need to arise to a torsional spring constant. Otherwise, the speed propeller shaft will not meet the design criteria. If it's not meeting the design criteria, what will happen to the system? Of course, it will just die down. No? It will just create vibration, and too much vibration can die down the engine, no? And damage the propeller itself, and return, you know, crash landing. So we need to consider segment 12 and 23. No? So we have to consider torque induced, no? Because we have a propeller shaft and torque applied at the propeller T, hence the elasticity spring. Again, we mentioned the three components of vibration: elasticity, spring, corresponding to the two segment 12 and 3 are to be considered as series spring. No? So we mentioned already series spring, parallel spring. So the spring constant of segment 12 of the shaft, no, are given by, okay, it's not found here, no? Okay, it's the one. Okay, example, no? So, but we go directly to the formula here. This is key spring, no? Deflection. So this is the formula GG over L, then the basic unit is N, no? And M per rad, no, radyan, no? So this is given from the this one, no, this problem here. So where is the problem? This one, example 1.3, no? So as you can see, you have a lot of values here: 0.3, 2 meter, 3 meter, point. And these are the x or y axis from your this one, the center, no, the shaft. So this is how you structure your frame here, no? And of course, it's attached here at number 1. So that this arises the problem now, no? Then the solution. So we have the spring constant. So it goes now here, no? As you can see, we have the value G phi. So G is 80. So what is not given here, no? 80. Okay, we just provide this 80 here times 10 pi 80 times 10, that G phi, then D, this diameter outside, and the small diameter divided 32, and moment of inertia is 2. So given L is 2. So it's not also specified here, but here we have 2 here, no? The distance, okay? So we have key at 1 to 2 and 2 to 3. Where is 1 to 2? 1 to 2 is somewhere here. 1 and 2. This one, 1 to 2. And then 2 to 3. No? So we are trying to solve the deflection near the spring. No? Spring constant. Okay, the value is 25 and 8.9. So remember the units. Okay, since the springs are in series, no? So you need to series K12, K13 divided by this given K12 plus K. So the total spring, no, equivalent is 6.5997 times 10 to the 6 Newton meter per rad. No? Okay, another problem is equivalent K of a crane, no? This one, you know what is an overhead crane, no? So you have total weight and the distance of the crane, arm, you have the pulley, CB and DE. So you have the distance between these two and the crane and this guiding, no? Rope here. Okay, the boom EB. Where is EB? This one, E to B, that is the boom, no? Is uniform steel bar of length 10 meters, so this is 10 meter, and X section area of 2,500 mm square. So that is the section area, no, of this boom. Okay. A weight W is suspended, no? This one. Okay, this carries the weight, no? While the crane is stationary, so it can be moving, but right now it's just stationed here. Tail cable, no? So you can see the steel cable, C, B, D, E, F. This one. So that's the steel cable that means to rotate, no? That's used to bring up and down the weight. A sectional area of 100 square meter, no? So what is section area? So the area itself, no? Section area. So it's round, okay? So neglect effect of cable CDE, BE, neglect the effect. Find equivalent spring constant of a system in the vertical direction. So again, when we deal with vibration analysis, it's not just like it's moving to and fro or moving up and down. It can be the work of a spring constant, a spring, no? Find the equivalent spring constant of a system in vertical direction. No? So what happens here? So spring constant is unknown. So a vertical displacement of x of pt, displacement x, no, this one x, no, of point B, this point B, will cause the spring keto. Where is spring keto? This one, Tito. Tension 2, no? Boom to deform by x2 equals x cosine, no? This one is an angle, no? Cosine 45 degrees. And spring K1 cable to deform by an amount of x1, no? This one, x cosine. So where is x? This one. Cosine 90 degrees minus 0. Length of cable FB, I1 is as shown. No? Where's the length of cable FB? So this one, FB. So that's I1 is as shown. So what is I1? So I1 equals I squared equals 3 squared. So what is 3? Okay, where's 3? So here, 3. Okay. 3 squared plus 10 squared. Okay, this one 10 squared. Minus 2. This one 2. So that's the formula. 2 times 3, 10 cosine 135 degrees equals 151.426. Conclusion, so this one, the length of cable FB, no, is 12.3055. So again, very important, no, and you deal with um, assessing, no, the proper length of a cable for a given weight. No? If the given angle of the boom is like this, so that you will know how to raise the weight to a certain distance from the ground to a height of the building. So you can determine, no, the length of the cable required in order to bring that height, that weight into a certain level. No? With this given vibration analysis, no? we with that knowledge, we come to realize now that even this kind of engineering problem has lead to the application of vibration analysis in order to determine the length of the cable. No? And that's, I think, very awesome, guys. Awesome. No? So again, the angle theta satisfies the relation. No? Okay. So this is the formula. So that satisfies cosine theta is 0.8184. Therefore, theta is 35 degrees. No? So here, where is 35 degrees? Somewhere here, no? Okay. So 35 degrees. The total potential energy we have already in the beginning, our formula, no? So first we get K1, then apply it here, so we can get the potential energy. So the potential energy is the energy while it at rest. No? So Kito deflection, we can solve also with this formula. So we have this Newton per meter. No? So deflection is for every meter you have the force. No, for every meter the deflection. So it means to say that is the the value of deflection, whether it can be raised up or going down. So that is the location of that deflection at a given situation. No? So meaning to say when it goes beyond that deflection, then might something, no? Something happen, no? Or go that deflection, maybe it cannot stand up the weight itself, no? So if going beyond, then perhaps um, it might topple, no? But if it's also short, it cannot also bring the weight to that certain level. No? It should have the proper deflection at certain potential energy. Okay, and that's how you balance things, no? And that's where vibration applies. Okay, so we go now to potential energy of the equivalent spring. Okay, that's the formula. For example, this is equivalent spring and the weight. So you can find the formula here. So potential energy is equal to equivalent energy. Yeah, we have also the mass or inertia elements, no? So let's start from here and we'll continue next time. But even though we'll start from here, we can still get some um, things, no, to consider in our prelim. If we have to schedule it, or probably we can move it to the next week, no, so that we can finish the entire thing. So we'll just make this as part one, and we'll give you part two next time. We are now ending at uh, slide 47 and still have to finish until 109. So thank you for listening, guys. See you next time around. Thank you. Bye-bye. Sakto ay.